Okay, we're ready to continue on tides. So I will share the screen here. The computer will do it. There we go. Okay, so dynamic model of the tides. Again, this is somewhat more complex, and not surprisingly, it's more realistic. Reality does tend to be complicated. So instead of our simple equilibrium model that had two bulges, one towards the moon, one away from it, the Earth turns under that. Now we have land, and we have the Coriolis effect, and this leads to our thinking about the tides as great big rotating waves. That will have the picture a little out of the way here. Here in the northern hemisphere, we're north of the equator, and so the bulge from the tides is rotating counterclockwise. You recall it's the reverse of the pattern for currents. The current gyres that we looked at are going clockwise here in the northern hemisphere, counterclockwise in the south. But for the tides, it adds up to going the opposite way, tides counterclockwise here in the northern hemisphere and clockwise in the south. We can draw a diagram to represent these rotating waves. And this is for an idealized ocean. Of course, real oceans are not perfectly square or circular, so they're going to be more irregular in the pattern. But this gives an idea of how we can think about the tide pattern. This diagram has two different types of lines on it. We have the circles, which are the co-range circles, and the radiating lines, which are the co-tidal lines. Co-tidal line means everywhere along this line has high tide at the same time. And so here, okay, 0 hours, that's our starting point. An hour later, along here has high tide. 2 hours later here, 8 hours, it's along there. And then 11, 12, we're going back around. So this is evidently some place that has either semi-diurnal or a mixed pattern, because it completes the cycle in just over 12 hours rather than 24. And you can get an idea, for example, okay, when's the tide high, say right in here? Well, between 7 and 8 hours after our starting time here. Of course, if tide is high along our 0 line, that means that it is low opposite that along our 6 line over here. So tide will be high out here and low out in the other direction. Co-range means everywhere on the circle has the same difference range between the high and the low. So in this case, our circle here has 0.5 meters. So the difference between high and low tide, if you're on that circle, 0.5 meter. Out there, it's a meter different. And this is not too surprising. Right in the middle, that very central point, is the node where things are not going up and down due to the tide. If you were right at that point, that would experience no tide, but of course, out in the middle of the ocean, it's not so obvious. And it's out to the edges with the greatest variation, which is where we live and where tide's kind of conspicuous. So we tend to see that our higher tides out to the sides. As an illustration of the importance of the form of the ocean basin, it's been calculated that the current width of the Atlantic, or plate tectonics, has changed over time, but the current width turns out to support having much higher tides than would have been the case going appreciably back in geologic time. So there are differences there. Of course, also you go far enough back and you have noticeable changes in how far away the moon is, and that would change the tides as well. So again, co-tidal line marks the part of the wave where we have high tide at the same time. Again, they're going to be more irregular in reality, and our co-range circles have the same tidal range from high to low. Our rotation pattern, again, clockwise to the south, counterclockwise to the north for the tides, not for currents. And we'll see how this relates to wind patterns later. Now, even our dynamic model has limits. It is simplified. It turns out with all the interactions between the sun and the moon and the earth, we have 65 different components all adding up to give the actual picture of the tides. We're not going to look at that in detail, but knowing that when you see a tide table, then you're looking at the components, all of those put together. So here are a few of them. We have the ups and downs from both the moon and the sun relative to the Earth for semi-diurnal, and also as the moon is going around the Earth, it's not a perfect circle. Orbits are ellipses, and so you get a little bit of variation due to the month. So all these different things add up to our actual tide. Remember, wave interference from talking about waves. So here's a picture of what actual tide cycles are like for major ocean regions of the globe. You see, for example, affecting our coast, if we make the high tide here in North Carolina, looks like that's pretty close to Cape Hatteras, as our zero, then that wave circles all the way around. It's already across high tide in Spain 2 hours later, and Portugal there. So tide waves are very big, very fast moving, but well, they happen every day, so you know they're coming. You should know better than try to build a house at low tide and not expect to get flooded at high tide. This is circling around. We see, yep, that's counterclockwise, as it should be in the Northern Hemisphere. Down here, south of Africa, here's circling, going 0 to 2 here, so that's going clockwise, typical for the Southern Hemisphere. Now, this is, again, a pattern that we see in a relatively open area. You may remember our dynamic model hypothetical ocean was a square. What's going to happen if we have a more narrow space that our tide is trying to go in? Tides can't rotate under those conditions. And so instead, our tide flow is going to be coming in, going out, in and out in these settings. If the bay is getting narrower as we go in, that's squeezing that water into a smaller space, and the tide may actually get higher as it goes in. If it doesn't do that, it's more parallel or maybe even getting wider, then our bay is probably kind of shallow. Friction that will tend to decrease the tide, but it depends on the shape. If, as our tide's coming in and going back out, at just the right time to meet the next wave coming in. That's the situation that we ran into with Seychelles. So this can create extra extreme tides. Situation is known as tidal resonance. Another distinctive phenomenon that occurs in these types of settings is a tidal bore. This is where we have the tide moving into a more narrow area, and you actually can see a wave front along as the tide is coming in. This particularly can be seen in certain rivers. Long, narrow area that connects to the ocean. Well, I said something about rivers. Where we have a river or other structure kind of entering into the ocean is a spot where we commonly see this type of thing happening. Another example would be a fjord, a flooded glacial valley where the water comes in, typical of colder parts of the world. There's a very famous tidal bore that happens when the combination of tides is just right in a river in China, and you get quite a lot of tourists coming to see it. Some are crazy enough to try to surf it, and that doesn't always turn out very well. A major problem with trying to surf something like a tidal bore, your ordinary surfing, here comes a wave, and ooh, you're riding it, and it's gone past, and you're hanging out waiting for the next wave. That's very different from something like a tidal bore, or in certain other settings, like in some river areas, where you've got a wave that is lasting for a very long time. That's quite a different style of using your muscles than the ordinary surfing, just like it would be quite different if you're preparing for being, say, cross-country versus sprinting. So somebody who thinks they've surfed some waves on the beach and are ready to take on tidal bore, that's different. Here are pictures, both simplified and real examples of patterns of tides in more enclosed areas. If our basin, say some sort of bay, is relatively even in its dimensions, then tide comes in out from the ocean here, and will go around in a rotating pattern pretty similar to our standard infodromic system. Here's a real world example. Up here in the Gulf of St. Lawrence, Canada. Obviously, that's not a perfect circle by any means, but it's reasonably even in shape. And so the tide comes in out here from the open Atlantic. Hopefully, the virus will be under control enough for me to go to a meeting there next summer. And then it's rotating around. Yep, it's counterclockwise. It's in the northern hemisphere. Pretty similar to our ideal open ocean pattern of the tides rotating around. But if we have a more narrow one, then again, our tides are going in and out, rather than our rotating pattern. The Bay of Fundy is a good example of that. Again, Eastern Canada, well, barely the edge of it. Maine's kind of over here relative to this map. And so you can see both the co-tidal and co-range lines are going in and out. They're not perfectly parallel to each other, but they're pretty similar. Here's a picture of a tidal bore. Again, with the Bay of Fundy, you can see the actual wave front here as the high tide's coming in. Most places you don't see the tidal bore, and it's just okay, the water is coming up. But again, some places that are somewhat more narrow, you see this wave front coming in. Another thing, again, Bay of Fundy, quite extreme tides. You see quite a lot of mud back there and a wide zone of marsh grasses before you finally see houses and things way back there. That's a hint that sticking anything in here is not such a good idea. The tide going up and down floods and exposes these back and forth. A lot of mud. It's not too easy living someplace that's alternating between being flooded and being exposed to the air. And so you have some grasses that can tolerate getting pretty wet, but not too deep down, that are dominating higher up here. And then the mud here, you don't have any plants able to grow on the mostly under muddy water most of the time setting, although there are going to be a number of types of animals that can make burrows down in the mud, hide in the mud when they don't like the conditions above, and come out when they like it, things of that sort. As the tide goes around, of course, out in the open ocean, circling around, well, that gives you a bit of a current, but it's just going in circles, so it doesn't have too obvious major effect. But as we get close to land, especially where there are channels, we can get distinctive currents coming in and out. These are referred to flood currents if they're associated with the tide coming in to high, and ebb currents if the tide is going back out to low. So the current in an area that has these will be switching back and forth between the tides, in and out, flood and ebb. As tides are changing, the flow may be quite fast, especially if there's a narrow channel, say between islands. This flow can get to be quite significant. It's something very important to keep in mind if you are at the beach and decide you're going to wade across a channel to get to the other side. It may be pretty easy to go across that channel right at low tide, but as the tides are changing, the current may be fast enough in there to wash you off your feet. So it's important to keep this in mind. Also, tides coming in, tides going out. Well, it has to turn around there. So we have slowing and stopping at high tide coming in, and at low tide going back and out again. So these points are referred to as slack high tide and slack low tide. Up and down, those are the times when basically the tidal current is still. Either the water is all the way in and getting ready to switch from in to out, or it's all the way out and getting ready to switch the other way. These are slack tide points. Tides, it's a lot of energy. Now it's also kind of spread out all over the place. But if we have a bay with a relatively narrow opening, there may be significant tide variation, and this can be a suitable spot for generating electrical energy, similar to the idea of the hydropower electricity from a dam. So this can be a useful option. At the same time, there are some challenges. Salt water, so you know if you've ever had stuff around the beach, tends to rust stuff. It's very not good for a lot of the mechanical parts. So you have additional challenges that you don't have for a freshwater dam. And of course, you want to make sure that having the dam there is not causing any particular environmental problems due to the effects it has on the local conditions. Not surprisingly, being someplace where you're alternating between underwater and exposed to the air makes a big difference for things living there. And so the organisms that live in intertidal zones, places between the high tide and low tide level, have ways of dealing with the situation. This is an example from a study on fiddler crabs. Some of the crabs were brought into the lab, and these crabs will hide down in their burrow at high tide to avoid all the swimming predators like fish that will be coming in with the high tide. And then at low tide, they'll come out of the burrow and run around on the mud or sand looking for bits of food. And the fiddler name refers to courtship, other things that they're doing there. Kept in the lab, a little tank in the lab is not going to have significant tide difference, but the crabs still maintain a distinctive timing of activity, showing that they have some sort of internal clock, though, as is true of most organisms' internal clock, it has to be calibrated by comparison with clues around. Just as our internal clock gets thrown off if, say, we're exposed to too much light late at night. Yes, that means it is a good idea for you to turn off your phone, not trying to keep it in touch all night. The crabs, by the tide coming in and out, can keep their internal clock in sync with the outsides and be active at the right times of day. Link is working well here. Yeah, here we go. These are pictures of fiddler crabs. All the ones so far here. Oh, there we go. So this one you see does not have big claws. This is a female. All these others are different types from around the world, males with that big claw. Somebody thought that waving around that big claw looked like a violinist, so that's where the fiddler crab name comes from. But in fact, that big claw is used to wave around to intimidate other males and impress the females. If something happens, say a predator gets a hold of it, it can drop a leg, including the big claw. At that point, the male's other claw will start to grow bigger, and the new claw that grows to replace the one he lost will come in as a small claw. The small claw is practical for eating, so we see the female is rather more practical than the male. These are pretty common along coastal areas in many parts of the world. If you go to a salt marsh here in the Carolinas, you're likely to see a good deal of fiddler crabs around. Here's another example of an animal whose behavior is very much tied to the tides. These are grunion. This is a type of fish found along the coast of California and nearby areas. And they actually swim up as far as they can on the beach at the spring high tide. So the highest high tides. And so they are spawning and laying and fertilizing the eggs. And the eggs get buried in the sand right at the high tide line there. Why do that? There are a lot of hungry mouths out there in the ocean. So by burying the eggs at the high tide line, they are safe from ocean predators. Now, true, some land predators can potentially come down and dig things up on the beach, but it's protected from all the ocean predators that could easily gobble up fish eggs that are just floating around in the ocean somewhere. Then at the next spring tide, that's given the egg a chance to develop, and the little baby fish can hatch out and swim off and actually swim, so it's a little bit better protected than just an egg floating. Tides, as very big waves, affect not just the surface, but on down all the way to the bottom of the ocean. And so that surface tide sets up additional waves that are internal waves below the surface layer. Turns out that the tide internal waves are quite important in promoting erosion of the continental slopes, helping to wash the sediment, sand, and mud down that slope towards the deep ocean. Basically, the issue is, depending on the angle that a wave comes in, it may tend to bounce off more, as the two left-hand pictures illustrate. But if that wave angle is just right to come smack into the bottom of the ocean, it's going to stir up sand and mud a lot more. And then that sand and mud in the water is going to tend to flow down before it settles out again. Turns out that the way tides work out, they tend to come in at just the right angle to really hit into your average continental slope. Okay, so that wraps up our look at the tides. And let's see. There we go. So finishing for this lecture series.